Welcome to our next video on condensed matter theory. Today I want to talk, or in this lecture I want to talk about the Hall effect and see how we can explain this within the Drude model. So let's start by having a look at what we actually do in an experiment where we measure the Hall effect. And we start with a bar of metal in 3 dimensions. And the bar has a length L, and I'll put the length in the x direction, a width W, and I put the width in the y direction, and a thickness D, and we put the D in the z direction, so that we have our axis coordinates. Then we put on a voltage over our bar, such that we get a current I, and on top of that we put on a magnetic field, and we put the magnetic field perpendicular to the bar, so in this case in the z direction. Naturally you are allowed to put different geometries and different angles, etc. You can all work this out, and these are just going to be geometrical arguments. But for our argumentation, this setup is the easiest, so let's just stick with this arrangement. If you do this, you'll notice that perpendicular to your current and the magnetic field, we'll get an additional voltage, and that is what we call the Hall voltage. Well, we can understand the Hall voltage. The electrons start to flow. In the magnetic field, they have a Lorentz force, so the electrons start to move in one direction, and therefore on one side of your bar you get an accumulation of electrons. Well, that doesn't continue forever, because these electrons start to generate an electrical field, and the force of that electrical field then pushes the electrons back. So first of all, the experimental observation of Hall was that your Hall voltage is proportional to the current, the magnetic field divided by the thickness of your sample, times the material specific constant. And let's see how we can derive this with the Drude model. So as we said before, we have a voltage because of the electrical field of the electrons that accumulate, and that force has to be equal but opposite in sign to the Lorentz force generated by the moving electrons through the magnetic field. Well, the force that is related to the electrical field that we measure with the Hall voltage is just minus E times the electrical field in the y direction, which is given in our case by the Hall voltage divided by the width of our bar. And then we have the Lorentz force on our electrons, which is given as minus E times the velocity that we have out the product with the magnetic field. And again, for the case that we have here, where the magnetic field is in the z direction, the velocity in the y direction, the force is going to be perfectly in the x direction, and this is given by the velocity in the y direction, x direction, times the magnetic field in the z direction. Such that we can set these two equal to each other. There is a minus sign here. Such that, well, they have to be minus each other, such that our Hall voltage is given by the width of our sample times the velocity of the electrons in the x direction times the field in the z direction. We can now see if we can relate the voltage, the velocity of our electrons to things like the current. And of course we can do that. We know that our current is given by the current density times the area through which that current density flows. And our current density is given by minus the electron density, the electron charge, the velocity of the electrons, and then we still have the area in there. We can solve this such that our velocity is given by minus the current divided by NE, the width times the thickness. We can now put this into the expression for the Hall voltage, and we find the width drops out, that we have minus Ix divided by NED times the magnetic field in the Z direction. If we now compare this, then we see that we can define the Hall resistance as minus 1 over the electron density times the electron charge. And that actually is a really nice expression, which only depends on the number of charge carriers that you have per volume and the electron charge. So if you look at the periodic table, and we start with the alkalides, metals. If you look, for example, at sodium, then you would expect that you have the 1s, 2s and 2p shell filled, but they will be strongly bound to the nucleus. So for a material like sodium, I would expect that I have 1 electron per atom contributing to the free electrons that we consider in the Drude model that form your free electron gas. So if we express the Hall resistance in units where we look at the number of electrons per atom that we have in a solid, so per volume of atoms, then we can look at the Hall resistance that we measure. We take the units of electric charge to be 1. So we have N per atom as obtained from Hall. And for sodium we measure 1.006. Pretty good. That's pretty close to 1 that you would expect from a simple model as we have here. We can also do this for potassium and then it becomes even better. Rubidium 0.927. Lithium, I should check if it's really this far off, but lithium, I know not everything is perfect, so that's 27% off. I might have a 0 missing here, but I'll have to look at later. So we see that actually this works really nice. And we can really use this to determine the number of free charge carriers that we have in our system. Now, people put in aluminum. And aluminum we find here in the periodic table. So again, the 1s and the 2s, 2p shells are filled. They are going to belong to the core. We now have 3 electrons in the NS3 principal quantum shell. You might expect that 2 electrons in the S shell become localized, in which case you would have 1 electron contributing per atom to your charge. They might also still contribute, then you would have 3 electrons. Now what do we measure? And what we measure is 1.0008. With a minus sign. The effective charge carriers, as you find them in the Hall, resistivity, well, we don't have negative charge carriers. So we should have negative charge. Or do we? It looks as if the charge carriers here are positively charged. So PhD students in that time had to look for new particles with charge mass ratios of electrons, but then positively charged. That's just weird. What is going on here? And actually, it took quite a time before people were able to explain this wrong charge of the charge carriers in a material like aluminum. It became even weirder and weirder as time went on because, well, the Drude model became the Sommerfeld model, where you have all the quantum mechanical ingredients, and it explained more and more properties. And this just stayed away. This just stays the way it is. And we'll explain this later in the lecture. Actually, we use this, that we have charge carriers with positive charge and negative charge. In our semiconductors, the transistors, the diodes, we take a semiconductor, which is, well, at low temperature an insulator, and then you dope it, N-type or P-type, such that you either get positively charged charge carriers or negatively charged charge carriers. And with those interfaces you can play and then also switch between having a conductive system or not. And that, of course, you then use as the switches we have in our electronics. And that's what the entire communication between us at the moment is based on. So far, we can explain the Hall effect, we get what we observe, and we do find that the Hall resistance is beautifully related to the charge carriers, which is also what the Hall effect is used for nowadays. But we find that, well, for several materials you get perfectly the answer that you should expect. It's not always highly accurate, especially if you would go to the transition metals, then you get numbers that are off, but reasonable given the simplicity of the model. But in some cases your charge carriers seem to have opposite charge as you would expect. Yeah, that's what I'm going to leave you with for today. We'll come back to that in 2 or 3 weeks when we have done the Sommerfeld model as well as the effect of the crystal lattice. And then we can come back and explain why we have positive and negatively charged charge carriers. Thank you very much. We see each other later. Stay healthy.